Energy. It's all around us. It's so special, seemingly invisible, but it's everywhere. We are energy, and we are surrounded by it. It runs our bodies, our machines, our countries. Well, for the most part. When we talk about energy, electricity is probably one of the first things to come to mind. Yet energy is so much more than just the power keeping the lights on. For many centuries, much before electricity became the standard for power transmission, our ancestors relied on a mix of clever systems to transmit energy to where it was needed. If you pay attention, you too will be able to find many examples of alternate forms of power transmission that we use today. In this video, we will look at pressurized water as a way of power transmission. We call this hydraulic power. I'll be covering other methods in separate videos. Make sure to check them out if you're interested. We can transmit power by means of ropes, cables and pulleys, so-called telodynamic transmission. Energy flowing along cables is what makes funiculars and cable cars move through space. These power lines, sometimes measuring multiple kilometers in a single section, function just like a massive mechanical conveyor belt. We also move power using air all the time, so-called pneumatic energy. There is also the opposite, not pressurized air, just some serious sucking. This type of power transmission powers pumps and all kinds of shop tools. One of the most impressive examples are these amazing wheel guns. Let's rewind a bit. Hydraulic power was already around when the pyramids were being built, whenever that was. The earliest documented use dates back to more than 8,000 years ago, in the fertile lands of Mesopotamia and ancient Egypt. There are certainly many uses that we will probably never know of, as this knowledge got lost in time. You can find examples of various uses of this all around the world. An extraordinary example showcasing an ingenious use of water is this elephant clock, created by Islamic engineer Ismail al-Jazari in the Middle Ages. This clock stood at 7 meters tall and contained a complex mechanism that functioned as an automatic, water-powered timer. A large bowl inside the belly of the elephant filled up with water slowly, a process that would take exactly 30 minutes. Once full, it would then sink to the bottom of the water tank, setting in motion a whole autonomous mechanism with many different pieces. No human interaction was needed. Sitting on top of the elephant, there was a humanoid scribe whose pen pointed exactly at the minutes of that current hour. This automaton sitting on top is considered to be the first robot ever created, which is why Al-Jazari is often called the father of robotics. To get a deeper understanding of this, let's have a look at what hydraulic power is. Hydraulic power is a way to transmit energy through water or any other incompressible fluid. Blaise Pascal, the French mathematician, philosopher, physicist, inventor of one of the first mechanical calculators, and the guy who basically invented public transport, yes really, look up the carrosse à 5 sols, had a serious moment of enlightenment while he was thinking about water. He found out that, unlike air, it's nearly impossible to compress a fluid. This is called the hydrostatic paradox. In other words, the deeper you go, the more pressure there is, and it's always transmitted in the same way in multiple directions. You can effectively multiply forces with very little effort. That's what allows you to lift a car using only your foot. However, the undisputable best application of hydraulic power only came almost a full century later.
The beer pump.
Joseph Bramah is the gentleman behind the beer pump, not the barman. His beer pump was an improved version of an invention made earlier by Dutchman John Lofting, who also famously invented the sucking worm, a water delivery device that used a rotary pump and a worm gear to create strong, continuous suction for efficient water delivery. This was used, for instance, to combat fires. As refrigerators did not exist back then, Bramah's beer engine allowed for beer and other beverages to be stored in cool basements and be pumped through a system of hoses to the bar above it, providing a fresh brew for everyone to enjoy. Bramah understood what so many overlook. Engineering excellence isn't always about brute force. Sometimes it's about applying just the right amount of suction. In the late 19th century, water turbines or water motors were being used across Europe and America. These water motors ran on any stream of water, be it from a river or on the city water coming straight out of the tap at home. The mechanical energy from the flowing water is then used to power machines directly, but sometimes also converted into electricity. A water motor is nothing more than a small turbine suspended in a metal casing. The diameter of the turbine could be of any size, be it small or large, depending on the intended use. As the water flows through the motor, it produces energy. However, since the water pressure is quite low, this only generates a small amount of energy, while using enormous quantities of potable water. Not that great for your water bill. The maximum output that you can get from a water motor is determined by two factors: water pressure and water flow. Increasing the quantity of the water by using a larger pipe is one way to increase the power capacity. The other way is to increase the pressure in the pipe, which yields much more interesting results because it means we could get more energy using less water. The smallest water motors were used to run ceiling fans, column fans, standing fans, fly swatting fans, exhaust fans, but not only fans. Almost everything could be mechanized, regardless of size. Water motors were also used for operating table saws, coffee grinders, elevators, ice cream freezers, church organs, sewing machines, industrial exhaust and ventilation systems, meat grinders, among so many more other things. Many of these applications weren't even new back then. Take a look at this hydraulis, for instance, a Roman water-powered organ. In 1883, the London Hydraulic Power Company started to supply power through high-pressure water from the River Thames, contained in cast iron mains. Similar systems were in use across the world, such as Liverpool, Birmingham, Melbourne, Sydney, Buenos Aires in Argentina, and Antwerp in Belgium. The main application for hydraulic power was for machinery that required great force, but had an intermittent and slow use, making it perfect for cranes, hoists, dock gates, bridges, conveyors, hydraulic presses, and so on. The Port of London and the railway depot were good for about 2/3 of the London Hydraulic Power Company's business. The remaining customers were factories around London and hotels, such as the Savoy, for instance. The Savoy used hydraulic elevators and even had a central hydraulic vacuum system called the Silent Dustman. Other notable examples include Tower Bridge, the revolving stages at the Palladium and the Colosseum, the safety curtains at Drury Lane and Her Majesty's theatres, and one of the finest examples of Victorian hydraulic stage engineering. The system, installed in 1896, used water-powered lifts and sliders to raise entire sections of the stage that were used to swap scenery and create dramatic effects, all operated with quiet, fluid power. Amazingly, this original machinery remained functional and was run one last time in 2019, just before theatre underwent its major restoration. A final encore for a hydraulic masterpiece that served the stage for over a century. The new high-power water system also brought environmental changes. Hundreds of workshops and offices that were previously using small but labor-intensive steam engines, that also produced a nasty smoke and made a lot of noise, changed over to a clean, quiet and reliable alternative, keeping the dirty air and noise at the pumping stations. At these pumping stations, the magnificent compound and triple expansion steam engines were responsible for creating the high pressure. The coal for the boilers was brought up the Thames by barge. This constant high pressure was initially created by tall accumulator towers, using only gravity. What made things much easier and cheaper was the invention of the hydraulic accumulator, a kind of giant battery. But this battery doesn't hold electricity. Instead, it works like a massive syringe with a heavy weight pushing down on a piston. This creates steady water pressure that can be released on demand. These hydraulic power networks could do what the electric grid of the time couldn't. Back then, electricity was still distributed as direct current, DC, meaning huge power losses occurred over distances longer than a few kilometers. The hydraulic system, by contrast, could supply serious power across an entire city with minimal losses. Also, since the water was used only for motive force and not for drinking, it could be pumped straight from the River Thames, further cutting costs. While Europe continued to develop these networks, the technology was mostly abandoned across the pond in favor of electricity. Even though these hydraulic networks worked extremely well, they were eventually phased out as factories began moving out of cities and the electric power became the standard. Still, the fact that London's system operated until 1977 proves that even the most dominant systems, like electricity, have viable alternatives. Thanks for watching. If you enjoyed this video, please like and subscribe. Unlike hydraulic power, this channel is very new, so your feedback and suggestions are very welcome. Let me know where you'd like this channel to go. Much of the research for this episode was inspired by the brilliant work of Chris de Decker over at Low Tech Magazine. A huge thanks as well to those who gave permission to use their footage and to the Internet Archive, a fantastic free resource which is worth supporting. Thank you all for watching and see you in the next one.